La Paz, Bolivia, and you see those guys are playing there. That's a cable car going. Look at all those cities. Now this is situated, the top part is 12,000 feet, goes down to 10,000 feet, 3,600 meters. And as you can see, this is a city like any other city in the world. But we are living this high. And by the way, this is propaganda for you to come over. I'm working for a tourist station. The population is 2 million people. Look at them go all around, shopping centers and all that. Everyday life. Now the question is, are these normal humans? They're living in chronic hypoxia, low oxygen conditions. So the title of my talk says, Space Travel in a High Altitude Environment, 9 psi and 21% oxygen, La Paz. Biology bypassing the pressure laws of physics. And this word that's very important, biospace forming. You know, when I prepared this talk about a month ago, a professor from the University of Barcelona asked me to write a chapter. And I said, oh, good, but I'm going to be busy. So I need a little bit of time. He said, no, you have 2 months. And I sent him my paper to this talk. And suddenly he sends me this paper, which I had not seen before, which is very interesting because it says the effects of 8 pounds per square inch and 32% oxygen atmosphere on the human in the space flight environment. Wow, that's amazing. So let's go. The good part about this is that you are going for a pressure that is a higher altitude within the space. Keep going. That's 15,000 feet of altitude simulate. You lower the pressure. But there's a problem there, and that's a red arrow, 32% oxygen. Because the idea is to reduce the pressure, but keep the astronauts at sea level oxygen tensions. But at sea level, it's 14 pounds per square inch and 20.9% oxygen. So I've looked into this, and this is a completely artificial environment. You know? You don't have this anywhere on planet Earth. So you have a balance. And this is nature. Oxygen 21%, nitrogen 79%, but of course, it's in the balance because it has to add up to 100, and that's life. If you tilt this and you increase the oxygen, you decrease nitrogen. And if you decrease nitrogen, whoa, I'm questioning. This can put the life of beings in space in peril. And I'm going to explain why. Keep going. 2 factors have been overlooked, carbon dioxide and hemoglobin. Now, I don't know if this is being established already in NASA, but it's good that I can give you this new thought about these things, a second consideration. So you see, La Paz is at 3,500 meters, and at sea level you have 98 millimeters of mercury, which is normoxia for all of you right now. If we take blood gases, we measure your oxygen, you have 98. If you guys have, right now, one of you has 60 millimeters of mercury, you're going to intensive care right away because that's too low for you. But for me, no, this is chronic hypoxia. I have been living here for over 53 years. I was born at high altitude, so this for me is normoxia. It is normal. In fact, coming down here, for me, is hyperoxia. And if I mess up here, it's because I have a little brain edema from too much oxygen. Believe me, it's true. Keep going. That's hyperoxia. Keep going. So at sea level, you have this oxygen pressure of 98, PaCO2 of 40, and you have an hematocrit of around 42, which is related to hemoglobin. And in the city of La Paz, with all that population that I've shown you, you have a pressure of 495 millimeters of mercury, which is 1/3 the pressure of the atmosphere, and you have oxygen tension of 60, and you have a carbon dioxide of 30. We already have 10 millimeters less of mercury of carbon dioxide. This is crucial, believe me. It's amazingly crucial. So, and of course, if you go up really fast, you will have acute mountain sickness, haze, maybe some of you will have, which makes all the people from all the physiologists of sea level fear of hypoxia. There's a fear, tremendous fear. But if you go up slowly, what happens is you adapt. You have adaptation. Look, if you go slowly, then after a while your hematocrit raises, your more hemoglobin, and then you have a remarkable adaptation to chronic hypoxia, which we call adaptation. And this is the city of La Paz. You already saw that. In the altitude cities of the world, we are defeating hypoxia. We don't worry about hypoxia as much as you guys do. We really don't. We're used to it. So, you see hypoxia up there, and I can punch it and get rid of it. That's why I wanted a Mac presentation, because it's a lot cooler. It falls down in pieces. But chronic hypoxia, for us, is a normal condition, okay? So, under this normoxia of altitude, why not have astronauts go in those conditions? That's the proposal here. Now that really scares a lot of sea level physiologists. Everybody says, you are crazy. I'm not crazy. Let me show you why. We're therefore proposing this normal Earth-found physiological condition. Physiological condition. We're adapted up there. Everybody adapts there for thousands of years. The first pillar is the adaptation formula. Okay, I developed this with my father, and what you have is, if you're at sea level, this is the hematocrit, and this is the time of days. When I go back, I was working at the University of Copenhagen, and my hematocrit dropped down to 36%, and when I went back, my mother said, oh my God, you're anemic, you must not be eating in Copenhagen. So when I came back, I started doing a lot of tests. I would spend 3 months in Copenhagen and a month and a half in La Paz, and then you can see that my red blood cells increased gradually, and it took 40 days for me to be in good condition. In this mid-range here, I would go up the stairs and be short of breath. After this, I can run up 8 stairs, not be short of breath. So that's my perfect adaptation, a full adaptation at the very end. And of course, this is normal life at high altitude. So hemoglobin plays a fundamental role in adaptation, without doubt. Everybody knows that. So we created this formula that's called adaptation equals time over altitude change. By the way, this formula adapts to everything that I've been hearing here today. The bone loss has exactly the same formula. Here we go, adaptation of the bone loss equals time over the amount of stress you are getting. It depends on the condition in space. For a fixed altitude like the city of La Paz, only the time factor of adaptation is significant. This means that we're not climbing mountains all the time. I mean, it's not like a mountaineer climbing that is going constantly up. You arrive in the city of La Paz, so the altitude change stops. Then you have the time factor of adaptation. So we have developed this 11.4 factor against a kilometer. You multiply by a kilometer of altitude, and you have 41 days for La Paz, and for Mount Everest, you would need 100 days. Keep going. Second pillar is the tolerance to hypoxia formula. I developed this formula, and it's very interesting because I looked at what makes us tolerate hypoxia better than sea level residents. And I figured that, of course, taking some data from populations, the hemoglobin would go up. This would be an estimated, which is just an estimation of Mount Everest. But anyway, it's going up. So that's a factor that is definitely there. The next one is the carbon dioxide. Look at the carbon dioxide at sea level here, and then going gradually down. This is Mount Everest. You see how it goes down? That's a fundamental thing. So from those two, I developed this tolerance to hypoxia formula or equation, where we have tolerance of hypoxia, hemoglobin on top, and arterial carbon dioxide tension on the bottom. In other words, the higher the hemoglobin, you tolerate better hypoxia. The higher CO2, you don't tolerate it. The lower it is, and that's what happens at high altitude, you tolerate much better. And then there's a constant factor that I can't explain how I got it, but let me show you what happens when this is ventilation and oxygen transport. When you're on the summit of Mount Everest or on the mountains, these factors play crucial things. These factors allow for the tolerance to hypoxia in our criteria. And look, this on Mount Everest, you can see that it's 7 times more tolerant to hypoxia. People have climbed to the summit of Mount Everest without oxygen. Recently, a woman climbed with no oxygen. That's the explanation. Please go. Third pillar, life is successfully carried out under chronic hypoxia at the city. That's it. You saw that already. So look at that city. You have to come over. Longevity at high altitude. You know, I asked for some data from the longevity table, from the local registration of citizens, and it turns out that this, like a guy like this, has been told has lived to 123 years at high altitude, 4,100 meters. And then they checked; it was not right. It was only 116. So keep going. This is a guy. Keep going. And this happens all the time. I keep hearing people that are over 100 at high altitude. And so this is the lower part of the Bolivia, Pando, and then I increase in altitude in meters all the way to Potosi, where the highest city is at 4,100. And look at this tendency for longevity, people older than 100. If you look at the older than 90, we have that. Of course, there's a beautiful city called Sucre. They have great wine there. So that's probably why they have much more longevity there. This is all divided by the population. And you see, this city and this city have 2 million inhabitants each. And this is at 416 meters, and this one's at 3,800 meters. Look at the difference between the 100 years old and over 90. Big differences. In my criteria, this is due to better tolerance to hypoxia. This is where we are, beautiful green planet, and this is where we intend to go. From an environment full of oxygen to an environment where there's no oxygen. So obviously, when I read that proposal, I said, it's going in the wrong direction. You don't have to increase oxygen for astronauts. You have to decrease it. Make them more tolerant to hypoxia. This is the future of mankind. Please. And we intend to go beyond in very difficult circumstances. Keep going. And that's, of course, the International Space Station. You guys are the experts. This is sea level. The pressure is 14.7. Everest is at 8,842 kilometers, 29,000 feet, 4.8 pounds per square inch. So astronauts need in space at 330 kilometers of altitude in microgravity, they need to maintain their physiology, and of course they do it in a way similar to Mount Everest's altitude there. I have some interesting proposals for this, but I don't have the time, but very interesting that can lower the pressures in there thanks to chronic hypoxia. So this is the altitude of La Paz, and that's 9.5 pounds per square inch, and that's about 1/3 less of the atmosphere, which is 2/3. But if you look at the pressure differences, you have 510 millimeters here of difference from sea level to this place in the spacesuit, which is 9.8 pounds per square inch. But if you look, just going from this altitude to this one, you have 4.7, which is half. In other words, if you're here, you're already gaining half of the pressure advantage. So this is chronic hypoxia, and I propose that it should go up there. It should go up there. And let me tell you why. Biology here is taking care of half of the pressure. So biology can help beat the laws of physics. That's amazing. So your starting pressure becomes that. By the way, I proposed many years back that you should move your Johnson Space Center to altitude of altiplan of 4,100 meters. Probably you save a lot of energy going out of, I don't know, let the engineers work that one out. Okay, so chronic hypoxia is the first step in one small step, but actually a giant step. Biology becomes a tool that bypasses the pressure laws of physics. And it's totally in a physiologic manner. It implies a complete change of mind frames. Chronic hypoxia is sustainable and even leads to longevity. So it becomes such a practical tool for an important biospace forming. Now this word, I created it thinking of what's going on, and these talks here were very stimulating to me. I feel very honored to be, and obviously I thank Alan for this beautiful opportunity to be here to express these ideas. But it's also been a great stimulus for me to be here. And Professor Dorta, I have to thank you also for allowing me to be present. And let me tell you, biospace forming is life, biospace forming. And I created this word because I think it's the adaptation of all living beings on Earth to space. And of course, in Spanish. And I think that we are struggling to keep humans in space as if they were in the playas of Varadero, okay? That's comfortable, that's nice, but I think reality, we have to be more realistic. So, when I wrote the paper, which I'll give you a link, the day it was published in India, it's about space travel, and I wrote the biospace forming. I said, oh, maybe somebody has already thought about this. So I looked it up, and I was the only one. So that was pretty comforting. It's not that way anymore. This is my father. He's the guy that gave me all that you're seeing here while I'm exposing to you. He was a physiologist. He's working with dogs' hearts. And he discovered that the dogs' hearts of high-altitude dogs were much more resistant than the sea-level dogs' hearts. This is our hypoxic adaptation chamber where we do studies in our institute. This is where the llamas are walking around Sahama, and we carried out a soccer game at 6,542 meters on top of this mountain to show you we survived. There you are, 6,500. Nobody died, 20 minutes per side. Sea level residents have one crucial disability. So you guys, you live with full of oxygen, and that's like you are lazy. You're not facing up to the challenges of survival. And so I think you have a poor tolerance to hypoxia. We are well prepared because we are forced to do it. We have adapted to it. But let me tell you, I'm a physician, and I treat a lot of the embassy people, even the American embassy and many embassies in La Paz. And a lot of them, when they come to La Paz, they're afraid to come to high altitude, but after they're there several years, they are very happy. Their children used to have asthma at sea level. They go up there, they don't have asthma. They really are adapting very well. In fact, the consul of the American embassy is a great runner. He's doing triathlon. He's doing this Ironman stuff at high altitude. This is my father. He proposed, and Alan knows about this, man can adapt to any altitude, even the summit of Mount Everest. He proposed this. This was a very bold idea because people only lived up to 5,000 meters. And so all sea level physiologists said, that's the highest you can survive. But he proposes, at that time, that no, it's not that way. It really is different because we see patients that have heart disease, have lung disease, and they live up there. babies are born with the pressure of Mount Everest, oxygen tensions, you know? So they tolerate it amazingly. So all of you have been in the womb and on the top of Mount Everest with the oxygen levels. So you're prepared. And this is, let me tell you, I was a visiting professor at the University of Copenhagen between 2004 and 2008. And the Professor Paul-Erik Powell, I was working with, he said, Gustavo, you know, this university should give you a degree because we made really good papers. They're very top trending now in our areas. Some of those papers are being used, have been adopted for the, I developed some nomograms to correct acid-base status at high altitude, and the Colombians use it regularly, which is really nice. And I worked all this with him. But let me tell you, most of you must be thinking, this guy, when he's talking about the other paper, he's looking into the idea, and he's kind of he's a copycat of that. Well, it goes the other way around. This was presented in 2007. In fact, in that dissertation that I prepared by invitation, I said hypoxic environment and space vehicles. Extravehicular mobility units could benefit from a lower oxygen tension, less pressure difference with the space capsule, and additionally more autonomy. I proposed all that. You know what happened? I got rejected. So he signed that. Look at this. And he says it cannot be recommended, it can be accepted. And look what he says, the relationship to space travel is awkward and not explained as to why this is relevant to high altitude hypoxia, because in space, the atmosphere of space cabin is similar to that of sea level on Earth. The effects of spaceflight on the erythrocyte volume are caused by weightlessness, which has nothing to do with high altitude benefits. The postulated benefits for astronauts reducing the cabin pressure or breathing before flight seems totally unfounded, very theoretical. So I flunked, okay? But I didn't copy the idea. Keep going. So this was published in 2013. Keep going. You know, after I got rejected, a German company called me and said, can we publish your dissertation? I said, sure, publish it. They got it from the University of Copenhagen, and they published it. And this is published in 2010, and it was written in 2007. So this is proof that I have been talking about these things. Maybe somebody else was thinking about these things, but I had to tell you what really happened. This is our 7th Chronic Hypoxia Symposium in La Paz. I invite you to join us. We do it every 2 years. We had a fabulous meeting this February. This is a Chacaltaya pyramid. We have a guide training there. It's at 5,250 meters. We can drive there in 2 hours. It's fascinating. Keep going. This is the paper that I was telling you, and when I used for the first time biospace forming. And let me tell you, biospace forming is truly what's going to happen to us. We're going to have to understand that we may not be coming back in some future flights. So we just simply have to adapt. I wonder, your talks were so interesting. When I saw that talk about Rana, your talk there of all these genetic changes, I wanted to ask you, but we didn't have time. Now, can I ask the question? No, kidding, we're done. You know, part of it is adaptation. Part of it may be deleterious effects of space travel. But I think adaptation is extraordinary. And we are adapting. We're constantly adapting, as my father has said. You cannot lose adaptation. You're always gaining it. So it's a matter of just adapting. And my gratitude to my father, of course. And this is all the people that I've worked with, families, relatives. The second one there is my daughter. She's a medical doctor. I was hoping to bring her. We couldn't coordinate it. And then all the family. So thank you very much. And I want to give this to it's a little book, a memory of my father, to Professor Dorta. And all of you, please, you're welcome to have one of those. I wrote that the night he passed away, so may have some mistakes. Oh, yeah, if we have just one let's say 30 seconds, just to give you a glimpse of what that was at 6,542 meters. It's a world record. They played this game and you see them running around. One of the balls went into the goal and went down the mountain. And press said it went down to sea level, but actually it was only to the base of the mountain. But it was a successful feat of how we adapt to hypoxia. This is 6,542 meters, less than 8 psi. Okay, thank you. Gracias.
Thank you very much. So I think we can have more discussions of this on the beach.
Yes. Yes, sure, no problem. Oh, gracias, Dr. Torta. Thank you very much. Muchas gracias.